Unit 1. The Structure of Geometry. Part C. Measurement. Lesson 3. Triangles. Objective. To understand and demonstrate the concepts of perimeter and area as they relate to triangles.
In this lesson, we are going to back up a little bit and consider measurements on triangles. The reason we started with rectangles was that the notion of area was more easily handled with that figure. I mean, the square units fit so cleanly. Now we know that if we can just make a rectangle out of a given figure, we can find its area easily. Of course, the first thing we want to do is to investigate the concept of measuring the perimeter of a triangle. What do you think? We have a triangle and we have measured the three sides. What do? That's right, just add all three measures. So what is the standard formula for the perimeter of a triangle? Good. The perimeter P is equal to the sum of the measures of sides A and B and C. Simple enough. Is there any way we can shorten that formula? Generally not, although it would be pretty simple if all three sides were of equal length. Right, that was the case with an equilateral triangle, remember? So if we know that the triangle is equilateral, we can just measure one side and triple it. In that case, the formula would read perimeter P is equal to 3 times S, the measure of one side. Either way, finding the perimeter of a triangle is pretty straightforward, isn't it? All right, let's see if finding the area inside a triangle is just as easy. Let's start with this special triangle. Do you remember what it is called? That's right, a right triangle. One of its angles is erect. It measures 90 degrees. It seems to have a base B and a height H, but once again, I can tell that the square units won't fit nicely into the interior of the triangle. What to do? Where are the scissors? We just find the middle point of the base and cut vertically, creating another right angle. Now take the piece we cut off, rotate it, and place it at the top, lining it up carefully. There it is, a rectangle. Now we can use our simple formula in which we multiply the base times the height. Wait a minute. The base of our new rectangle is only 1/2 the base of the original triangle. So our formula must be modified slightly. The area A will be equal to 1/2 the base B times the original height H. That makes sense. This triangle really was only half of a rectangle with base B and height H. Now substitute and tell me the area inside this triangle. Good, 36 square inches. But it does make me wonder, what if we cut it a different way? Let's start over. Here's our original triangle with base B and height H. This time, take the scissors and find the middle point of the height. Now cut horizontally. Rotate the piece you cut off and fit it neatly on the right side of the triangle. What is the formula now? That's right, the area A is equal to the base B times 1/2 the height, H. So what would the area be now? Of course it's the same. It has to be, doesn't it? It's still the same triangle. So how is the formula affected? Exactly, it's the same as well. Remember the commutative property of multiplication? It says that you can move numbers around when you are multiplying without changing the result. The formula is the same. All right, what about this triangle? It isn't a right triangle, is it? Do you remember what it is called? That's right, an acute triangle. All of the angles are acute angles. They all measure less than 90 degrees. So what about its area? We can still see a base B and a height H. Of course, to make it measurable, we need to cut it up, right? All right, cut across the triangle through the middle point of the height. Now rotate the piece you cut off. What do you have? Exactly, a parallelogram, which could be cut one more time to make a rectangle. And how does its base compare to the base of the original triangle? Good, it's the same. And how do the heights compare? That's right, the height of the rectangle measures 1/2 the height of the original triangle. So once more, the area of the triangle can be found by computing 1/2 the product of the measures of the original base and height. The formula didn't change, did it? Remember this triangle? Very good. It is an isosceles triangle, and the base and height have already been highlighted. You're already ahead of me, aren't you? When we cut off the top, rotate it, cut one more piece off, and move it to the other side, we see the same approach to finding the area. And this triangle? That's right, it is an obtuse triangle. One of its angles measures greater than 90 degrees. So what is its area? You use the same technique, don't you? No matter what type of triangle you are working with, no matter what the triangle looks like, or the way it's positioned, once you identify a base B and a height H, you will find the area to be 1/2 the product of the measures of the base and height. I hope that really makes sense to you now, and that should make it much easier to remember the standard formula for the area inside a triangle. Just remember that a triangle is really just 1/2 of a rectangle or parallelogram. Now give the exercises in the work text some attention and be very careful with your computation.